Welcome. My name is András Benczúr. I am the scientific director of the Hungarian Artificial Intelligence National Laboratory, a consortium of 11 institutions in the country. I lead the data science research lab at the Institute for Computer Science and Control in Hungary. This tutorial is joint work with three of my current and past doctoral students, Ferenc, Béres, Domokos, Kelen, and Róbert Pálovics. Robert is postdoc at Stanford University. Ferenc and Domokos work in my lab. Two very closely related work of my team is hands-on tutorial open source online learning recommenders from Rexis 4 years ago, and we co-authored 4 chapters in the Encyclopedia of Big Data Technologies on online machine learning in big data streams. We will make some mentions of these past works in this tutorial. If you want to follow the example Python codes in this tutorial, I recommend you check out the GitHub link of my colleague Ferenc, which contains all the resources. You can follow all the codes that we show in this tutorial. The tutorial is about temporal networks that change over time. These changing networks can be defined as an edge stream. The stream consists of a time series of edges. Each link, each edge has a timestamp, as you see in the example on the right. Edges may occur several times. One example of such a network is the Twitter mention network. If you look at the example, at time t1, user A can mention user B, then user B can mention user C at time t2, and so on. The first results on temporal networks usually considered static network snapshots with long-term changes. For example, some seminal works Kumar et al. In 2010 described the structure of and the evolution of online social networks. Their research considered Flickr and Yahoo community, and they considered changes in time. Another result by Roswell and Bergstrom mapped change in large networks considering scientific citation structure. They considered a decade of publications, and Sun, Falutzos, Papadimitriou, and Yu in their GraphScope paper mentioned graph streams, but actually they considered several networks with 50 to 1,000 incremental snapshots in different graphs. What we consider the first real temporal network model paper is by McGregor from Sigmod 2014. They consider streaming and semi-streaming algorithms for several graph tasks, including connectivity, sparsification, spanners, spanning trees, breadth-first trees, matchings, and so on. Some temporal network application results in the literature include social interactions considered as temporal networks, for example, retweets in Twitter with corresponding hashtags to track the popularity of political parties during an election period in the result of Aragon and his co-authors. Or network of cryptocurrency transactions can also be analyzed for assessing anonymity in our own works that we will describe in this tutorial, assessing Ethereum mixer anonymity, or tracking Bitcoin transactions in the blockchain to follow the route of a coin, of a payment, or analyze the Lightning Network, the Bitcoin overlay. One very important application is temporal graph queries in databases, where the goal is to find and online update frequent graph patterns. Most of the related results in the area, I will mention two, build and maintain and update various indexes. For example, Sasha Wang and Guino in Part1 2002 consider tree and graph search queries, and they use direct indexing of the most frequent subgraphs. And the streaming version of retrieving graphs quickly from a large database uses path indexing in the result of Yan Yu and Han from Sigmod 2004. The structure of this tutorial, this is part 1, a 60-minute tutorial. After the introduction, we will continue with showcasing a Twitter graph stream generator. Ferenc will present Python code that fetches Twitter data and on the fly generates the @mention stream from Twitter. Then I will continue with basic graph algorithms, for example, triangle counting in edge streams. Then Robert will talk about link prediction by online machine learning using the AlpenGlow toolkit that was part of our Rexis tutorial 4 years ago. And I will finish this first part by defining the notion of temporal walks. After 15 minutes break for question and answers, Ferenc will continue with online graph embedding algorithms and give an experiment on a Twitter collection. Then Robert will describe an online network centrality algorithm on the same dataset. And finally, I will close the presentation by giving an outlook, conclusions, list again the important resources. So now I let Ferenc continue.
Hi, my name is Ferenc Béres and I also welcome you to this tutorial. I prepared a demo to show you how to extract graph stream from Twitter data. If you are familiar with Twitter, then you know that several different graphs can be extracted from Twitter data. For example, there is the follower network where the nodes are accounts and the links are follower relationships. You can build a retweet graph from tweets and retweets. But now in this demo we will focus on the @mention network where the links are extracted from the tweet text. Nodes will be the Twitter accounts and the links between them are the @mentions extracted from the text. For example, user A posted a message with mentions to user B and user C. And on the right, you can see the corresponding mention network where there is a link from A to B and the link from A to C. If we want to attach time to the edges, then both of these edges will receive the same timestamp as they were mentioned in the same tweet. It will be the time when user A posted this tweet. We implemented a small streaming framework to showcase how to extract data with the Twitter streaming API. This framework has two components, a producer and a consumer, and they are connected with the socket. You can find the implementation on GitHub. And now let's dive into the Python code. On the right, you can see the Python implementation on the producer. It will have two main tasks. First, it will output the collected tweets to a socket. So first in the code, we will set and initialize the output channel, which will be a socket. Okay, and we will have one requirement, which is that we will only export tweets to the socket if it contains a mention. So it is specified during the initialization phase. Then we set up the Twitter crawler, which is connected to the Twitter streaming API. And we also set the search query, which will be 3 hashtags related to latest news. So basically, this crawler will collect tweets in real time containing any of these hashtags in English. And these tweets will arrive in real time and will be pushed to the socket when we run the crawler. Now let's move on to the consumer component, which will receive the tweets that were pushed to the socket by the producer. Then it will extract each mention from the tweet text, which is basically a dictionary, so we can access the mentions through keywords in Python. And then we will print the links of the edge stream to the console. As we discussed before, the links of the mention networks are Twittered mentions. The source node is the user who posted the tweet. The target node is the user who was mentioned in the tweet, and the timestamp for the edges are the time when the original tweet was posted. In order to see the code in action, first we start the producer in the bash console by specifying my Twitter API credentials in a JSON file and the port for the socket. Then we start the consumer in a different console by specifying the same port. Now we can see the graph stream printed to the console. For each mention, we print the timestamp, the source node, and the target node. These are the edges of the Twitter mention graphs. As we collect the data in real time, the data frequency is always changing based on the current Twitter activity.
After seeing this hands-on experience with a graph stream generator, let's take a few steps back and look at the theory of algorithms on data streams. This short part of the tutorial is based on our chapters of the Encyclopedia of Big Data Technologies. I list 4 issues with working with data streams. First and most important is the limitation of the computational model. We can only store a fixed amount of the data, not the potentially infinite entire stream, so we have to work from only some kind of snapshot, sliding window, or sample. Another and less known issue is that certain evaluation methods for machine learning methods fail, because once we train a model and give a prediction, new data comes which update the model, and in the next evaluation step we may have to consider potentially a completely different model. Very related issue is that concept drifts can occur, so we have to keep changing our model in this data stream. And finally, but we only mention as an outlook, we have to look at scalable distributed systems for processing the streams. Let's look at the first issue, the algorithmic limitations first. Considering the example of machine learning in the data streaming computational model, the main problem is we have no access to probably the majority of the past data, only we can store a small sample potentially. So for example, we have no stochastic gradient descent methods because we cannot iterate over the past data. What's still possible actually is online gradient descent. We can take gradient descent steps in the order the data arrives, but only once with every data except for possibly a small sample. It's difficult to make a decision tree algorithm. After we decide about the split in the decision tree, we cannot use the data inside the new leaves for constructing the next split. So what we can do, if we are statistically confident about the split, seeing some data, we can build further splits only by using the next data. and we can use concept drift statistics to rebuild certain branches. Another illustration of the computational model, if we consider the task of constructing the histogram of the stream and the number of times certain elements appear in the stream. If we're looking at the typical in-memory model, we can just build a hash table and use this hash table as a counter. If the data doesn't fit into internal memory, we can still do it on the disk, for example by sorting using, let's say, merge sort and then aggregating to get the counts. More difficult is the distributed version when the data does not even fit in a single server, so you have to split it in several servers, but that's the MapReduce computational model, which is basically sorting again. The main question is, what can we do with the data stream? So we want to compute the number of different elements in a data stream. And here's one very surprising algorithm. There's no exact algorithm without storing all the data, which can relatively easily be proved by looking at the trivial information bound. If we just want to decide if the next element is new or already present in the data stream, so we limit to only answering the 1-2 question. What we can do is we can reconstruct the entire past data stream by using a set of probing next elements, so that's an information theory bound. Another even more surprising fact is random sampling feels very bad. It's because of rare elements, and it's relatively easy, not very easy to construct a proof. We assume the sample consists of identical elements only. Then the likely answer is there are no other elements, so one single element appears n times. But we may have with large probability a large number of very rare elements that appear only once. And we can even build up a numerical example. So if we take a 20% random sample, which is almost the entire stream, it's the same order of size, we can construct data stream where the relative error on the count is more than 20%. This is a result that appears in Muthukrishnan and others' work, survey work on data stream algorithms. What's actually the solution is the so-called distinct sampling algorithm. We may read all the data, but we can make adaptive decisions on constructing the sample. The second issue regarding algorithms in data streams is it's less known. It's the difficulty of machine learning evaluation. What happens is the machine learning model changes right after a prediction is made and we see a new data sample. Traditional metrics such as precision and recall compare a set of predictions against the ground truth, but for the next prediction the new model may potentially give a completely new set of results, so there's no single set that we can compare. Actually, a natural streaming evaluation metric, if we think of the recommender system task, is the click-through rate, which is equivalent to the precision of a single item. It's a very strange notion. If the next item is clicked, then we have a plus. If not, then we get 0 reward. Another favorite metric that's very difficult to define for the streaming setting is, for example, UC. There's actually a methodology for evaluating classification in data streams, and it's a very old story, and it's not very well known, but it's been published already in 1984, and it's called the name of a prequential, it's short of predictive sequential evaluation, which means we give a prediction for the next data point, we read its label, compare the prediction, and update the quality metrics. And next we can update the model, and we can use a new model potentially a better model or a better adapted model for the next data point, and we need slightly modified metrics that we will discuss soon. And finally, regarding the issues of stream processing, concept drift is actually a case when online algorithms can even be better. Let's look at an example again of a recommender algorithm. On the graph on the right, we compare recommendation performance for standard research dataset coming from Stanford. What happens, we all know it very well, if we make a predictive model, its performance will deteriorate in time. So for example, we weekly retrain our models. If we look at our graphs, we see peaks, that's the freshly trained model, and then the performance deterioration. So concept drift detection can either detect sharp changes in the distribution or measure the deterioration of the scheduling retraining, or we can even do an auto forgetting of the old events. But what's surprising, if we take an online gradient descent algorithm that only uses the data points in the sequence, we get a much better performance than the batch versions of the model. Given this theoretical background, next I'd like to continue with some basic graph algorithms. Graph algorithms in H-streams considers computing various statistics of the graphs, the simplest example of the degree or its temporal variant, or other statistics, for example in the paper of Kim Anderson, only snapshot-based metrics are computed, but for relative complex notions such as closeness and betweenness centrality. Or we may use graph stream algorithms in database queries, for example, finding the node with maximum degree, the largest connected component, or the node pair connected by the largest number of paths. These all come from practically important database queries. To consider the example of temporal degree, we may add time decay to the degree. For example, if we give an exponential decay in the form of beta times an exponent of a constant times the time elapsed as a function of the age, that's a notion that diminishes fast, so we can only keep the recent edges, which makes the computation efficient. And it's got another important useful property that if we add the time, then we multiply the decay, so it's easy to update the decay as time elapses, multiply by phi of the additional time elapsed, and it can even give way to list of edges of walks because of this strange additive property. And the time decay degree performs very well for several tasks that are explicitly mentioned in this paper, so there are good applications already of this very simple graph statistic. Closeness and betweenness centrality, to look at the definitions first. Closeness centrality is the sum of 1 over the shortest path distance, and we can take a temporal variant of the shortest path. If we're considering only snapshots, it's easy to define. It's less easy to give an H-stream definition. Betweenness centrality is the proportion of a shortest path passing through the given node. Again, regarding snapshot versus graph stream model, we have the same issue. So the version of the Kim Anderson paper considers only temporal snapshots and actually incur very high computational costs and give no easy updates for these metrics. Triangle counting is a very actively researched algorithm in streams, We can even consider it as the hello world task of graph streaming algorithms, but it's got a very important application. It's the clustering coefficient, whose definition is the number of adjacent edge pairs divided by the number of triangles. Or we can say it's the fraction of the closed triangles. I just mentioned two important papers in the area, and I briefly sketched the idea of the second one, the so-called TREES algorithm, triangle counting in edge streams. The idea is to maintain a reservoir sample at time t at the current edge to a sample of size m with probability n divided by t, and update the neighborhood counters of this new sampled edge. And if the sample is full, we have to discard one edge and update its counters. And the key idea is to construct an unbiased estimate of the triangle count based on the neighborhood counters. It's the standard stream sampling trick, and the key is the construction and the analysis of the estimator. We have to give an estimate of the mean and of the variance. This method for triangle counting already introduced graph sampling and an additional sample of graph sampling results. The first results are typically semi-streaming, so not the fully graph streaming model, Feigenbaum, Kelen, and McGregor from 2005. The paper of Laskowitz and Falutsos from KDD 2006 lists algorithms and criteria that has to be maintained by the sample, both in static and in temporal graphs. A result of graph sketching for query estimation is given by Zhao and co-authors in 2011. And for example, graph priority sampling, it's an order-based reservoir sampling, is a more recent result by Ahmed and co-authors for 2017. After this brief list of interesting edge streaming graph algorithms, I give word to my colleagues. Ferenc will first introduce the research dataset that we collected from Twitter, and Robert will continue with the link prediction task. The task is to predict the next element of the stream, or rather the next edge adjacent to a node in question.
In 2017, we collected two Twitter datasets related to tennis championships, namely the Roland Garros and the US Open tennis tournaments. From the start, our intention was to develop new online algorithms that can detect relevant nodes from the edge stream. In this Jupyter Notebook presentation, I will focus on our results related to online node embedding. To ease the interaction with the collected data and the algorithms, we've published a Python package called Online Node2Vec, which can be downloaded and installed from the Python package index. From now on, I will show code snippets from the notebook, which is a good guideline to deploy our online node embedding models. As you can see, after the import, you will be able to download the data and process it only with a single function call. In the next slide. For this presentation, I chose the Roland Garros Twitter dataset, and we downloaded the data and preprocessed it with the download dataset function. After the preprocessing, we get back the directory where the preprocessed data is found, as well as a handler object, which will help us in further visualization tasks. The first component of the preprocessed data is the edge stream. As we discussed before, in Twitter mention graphs, the links are dimensions between Twitter accounts. After the preprocessing of the data, the edge stream is provided in the following content. In the first column, we can see the timestamp for each edge, which is followed by the source node ID and the target node ID. The distribution of the mentions change over time. For example, in the qualification phase, there is much less mentions, there is much less daily mentions than further on in the main tournament phase. It is also interesting to see that there are 3 spikes at the end of the data, which are related to the quarterfinals, the semifinals, and the finals for men's single tournaments. The distribution of the daily active nodes follow a similar distribution. The second part of the pre-processed data is the event schedule that we downloaded from the official event website. It contains information about the daily games and players. There is further metadata related to the match scores, the results. We know the type and category of each game, whether it is a men's game, a women's game, a single or a double tennis game, and we also know the court identifiers where these games have taken place. In our experiments, we use the information about daily tennis players to assign a temporal relevance label to every Twitter account in our dataset. But first, we needed to link tennis players to Twitter accounts. To be honest, it was the most time-consuming part of the data collection process. Now, we have the event schedule, the mapping from tennis players to Twitter accounts. So, next, we assigned a temporal relevance label to every Twitter account in the data. This binary relevance label changes from day to day, and it represents whether the given Twitter account is related to a tennis player who played on the given day. We call these accounts active accounts for each day. For example, as the code snippet shows, for the last day of Roland Garros, we have 18 active accounts in the data. After data preprocessing, it is easy to load the relevance labels.
In this part of the tutorial, we will consider the online ring prediction task. The dataset that we will use is the Roland Garros 2017 Twitter crawl, which consists of @mention events between Twitter users. Each of those can be considered as a directed edge between a source user and the target user. The first pre-processing step then that we will take is to filter out the organizer account from this dataset. If we simply list the most frequent users within the data and list them by the number of interactions that they have, this account specifically pops out and corresponds to roughly 100,000 of interactions within the data. This may heavily bias the final downstream experiments, and hence we decided to discard this account and all of the corresponding interactions from the dataset throughout this tutorial. In order to provide an overview of the data, here we show the number of events per day throughout the tournament. Those are increasing in the first 7 days and also have a high peak at the very end of this contest. We will use then this filter dataset to examine the online link prediction task. That specific problem is based on the predictive sequential or so-called prequential method, where for every single instance in the data stream, first we query the model to provide a node-specific or general link prediction, which is essentially a top list, and then we immediately evaluate this by using the observed actual instance within the stream. Once this evaluation is done, we allow the model to be updated then on this new instance. We can simulate this streaming scenario on an offline dataset by iterating through its records in a time-respecting order and conduct these two evaluation and training steps, and always start with the evaluation step. Note that throughout this tutorial we'll generate source-specific personalized predictions. In order to examine link prediction, we'll use Alpenglow, which is a recommender system prototyping tool with pre-sequential evaluation. The power of Alpenglow is that it can model various online and batch training scenarios. I recommend you to check out the project's GitHub page. Well, one may ask why a recommender system framework, and while apart from pre-sequential evaluation, we must note that Rexy-specific collaborative filtering data is actually represented as bipartite graphs. Apart from that, directed graphs are often modeled as bipartite graphs, surprisingly as well, especially in case of node embedding methods, and hence we can just use all the power of Alpenglow and provide node embedding based, for example, node embedding based link prediction models. There are several models implemented in Alpenglow, and one can experiment with those over the data of choice. For example, within the context of this data, first let's create a simple in-degree based prediction. Here, basically we record the in-degree of each target node, and then at each stream event we predict nodes with the highest in-degrees. This is called a popularity experiment within the context of Alpenglow, where we set top k equal to 2. Top k is a key parameter observed in every single experiment in Alpenglow, which basically restricts the length of the predicted top list from the implemented models. Once we define an experiment, we can run it with the run method, and then the outcome of a single experiment are rankings. These rankings encode the rank of every single stream event within the predicted top list. So basically, at the end of the day, the length of the retrieved rankings are the same as the length of the input data set. The evaluation of those ranks are then based on the online version of discounted cumulative gain, DCG, which is basically defined per event, and then per ranking of each single event within the stream, we can compute the DCG value, and then we can average these DCG scores over time. For example, we can create a final average throughout the whole data set, or we can create here, in case of this data, daily averages, and then visualize the average daily DCG scores throughout the tournament for a specific algorithm. This is great, since then we can just track basically the performance of the algorithm of choice over time. A highly successful and popular method for link prediction is based on node embeddings. We can create simple shallow embedding methods in Alpenglow and base our predictive scores for specific link of interest as the dot product of the corresponding source and target embeddings. This can be done by creating a so-called factor experiment. Here, after setting again top k equal to 20, we can set key parameters of the embeddings, such as their dimension and also the learning rate, negative rate parameters, which control the learning scenario of these over the simulated data stream. We can then run in a similar way as before the experiment and then compare the final DCG values over time between the node embeddings method and the in-degree based method. We can observe here that node embedding based prediction generally overperforms in degree, and hence these shallow embedding methods just better capture the data set and forecast which links will appear in the future. However, we must note here that this initial data consists of several duplicates over time when links and mentions just reappear over time. We can then filter for those duplicates. This will result in a radically different task, where we basically only consider the very first appearance of each link, not just for training but also for prediction, and hence the task will be to always predict the first appearance of each link within the data stream. Once we do the data filtering and rerun the algorithms we previously described, the results will be similar yet a bit different. in general, the gap between the two algorithms will be less in this different link prediction problem. A key task when simulating streaming offline is parameter optimization of the various algorithms of interest. Here we provide a snippet for optimizing one key parameter of a shallow embedding model, which is the learning rate which is applied during online learning from the data stream. Here we examine the performance of the shallow embedding method at 6 different learning rates and then just compute the global overall average over time at these different learning rates. We can conclude from this figure that the learning rate curve saturates around 0.3 and high learning rates around 0.3 and 35 are applicable on this dataset when running a shallow factorization method. Apart from experimenting with the models already defined in AlpenGlow, there is a potential possibility of defining your own custom models within this framework to experiment with those then. Basically, the definitions here follow the concept of frequential relation as described before. So on the Python code level, one can define its own model with the prediction and online update steps of frequential evaluation, and once these are done, one can just rerun this new custom model and experiment with it. To provide a template for these implementations, we basically re-implemented a shallow embedding model at the Python level within this framework, and following this implementation you may create your own models in AlpenGlow. In this final figure we show the predictive performance of this Python model, and one can see that the final results are somewhat comparable to the original shallow embedding model, which is provided by default in the framework. There is a potential way of combining different algorithms in AlpenGlow. This might be relevant in case of link prediction, since if we revisit the predictive performance of the two methods we investigated, the in-degree and the node embedding based one, we will realize that on different records are these two algorithms actually predictive. There are a few records where the in-degree based model is predictive, and there are another set of records where the factor model is predictive, and although there's an overlap of these, there are several records where only one of those models are actually predictive. And we can actually try to address that. One potential limitation or problem which could be the root cause of that is the so-called cold start problem, which may limit the predictive performance of the node embedding model. To address that, we can implement a custom model in AlpenGlow where for the very first few interactions of a user, the in-degree based model will try to predict, and then once the user has a few interactions already, we will switch our prediction and we'll base it on the node embedding based model. We can create that again by creating a custom update and prediction function, and we provide this very final code of the tutorial in AlpenGlow to address this custom combination. And then in the final side we just show the predictive performance of this combined model. Thank you for your attention.
In this previous part, we used matrix factorization for link prediction in temporal networks. The next results that will come in the second part of this tutorial will be based on the notion of temporal walks. We will use temporal walks to model the information flow in the network, which we will then use for embedding the network in vector space and also for defining centrality in the network. I will introduce the notion of the temporal walks at the end of this part of the presentation. These temporal walks are actually time-respective paths. Adjacent edges in the past have to be ordered in time, which we can consider as modeling an information flow in the social network, or it can be the flow of funds or goods in the economy, for example, in a cryptocurrency network. The concept is if the delay is small between two adjacent edges, then it's more likely that there is a flow of information, goods, funds, whatever on this path. And we assume there's no flow in the opposite direction, so from a future edge there's no information, no currency moving to a past edge, which may or may not be valid, but that's our assumption. In this example, we see temporal walks that end at node u before time t. We have 5 edges in this example, from A to B to C and then to U. These are ordered in time, so there's a temporal walk A, B, C, U, and the suffix is B, C, U, and C, U. And another walk that comes later at time T4 and T5, DE, and also the suffix EU. Our goal is to give weights to walks, and here we record the definition of the temporal degree with the decay function. For a temporal walk with edges that come in times t1, t2 up to tk for k edges, and certain decay function phi, we would like to define the weight of the entire walk as the product of the individual decays. And again, it's very beneficial for using the exponential decay. The exponent as the function of dh tau of the edge. So one advantage, if we recall, is we can only keep the recent edges and discard the old. And another thing is the product property, which is one benefit is to easily updatable for changes in time elapses. We can just multiply by the function of the elapsed time. And another thing is we can easily compute the weight of a list of edges that will simply be the decay function of the first minus the last edge in this above example. To use time-respecting walks in part 2, we will first consider walk-based network embedding methods by replacing the normal notion of non-time-oriented walks with temporal walks, for example, changing the node-to-vec algorithm of Gruber and Leskovec to one using streaming walks. And walk-based centrality, the idea of using temporal walks comes from the result of Rosenstein and Gionis, the temporal PageRank result. Our result that we present in part 2 will be based on the CUTS centrality. That's also a walk-based metric. To summarize the first part of the tutorial, we surveyed results and that analyze and model edge streams with examples of interactions in social network services and even queries in graph databases. The ingredients that we presented were the data streaming computational model, the notion of temporal networks, recently the temporal walks, and very importantly the frequential evaluation that allows us models that keep updating their model immediately after seeing new instances, and at every prediction step we evaluate actually a different model. And in the second part we will turn to more algorithms that update the results while the edge stream is processed. First, Ferenc will present network embeddings and an application for similarity search, and Róbert will present network centrality algorithms. We would like to thank you for your attention in this first part, and we will continue after the question and answer session.